All right, now we will continue our discussion of fluid properties. Another property is called the compressibility, and it refers to the change in volume of a substance that is subjected to a change of pressure in it. Okay, so the way to measure this compressibility is in terms of bulk modulus. And compressibility is actually another property, but the way to measure that is in terms of bulk modulus, which is just equal to E is equal to negative delta V over V sub 1, right? So change in pressure, divide, that's in negative, right? Negative change in pressure divided by the change in volume over the original volume. So that's the reason why I put a subscript of 1 here. Okay, so this bulk modulus is basically a reciprocal of the compressibility. Now, where can we find this? You can find this in tables and computations. We can calculate if you'd like, if we have data. Okay, so since this is a pressure, then that's in pascals, or let's say Newton per meter squared, and then this one, change in volume, that's just let's say meter cube divided by meter cube, right? So that's the unit of it's related to, or it's the same as the units for stress and pressures, right? Newton per meter squared or pascals. Okay, now there are still other properties but we'll not be able to discuss it here because I just choose to include the properties that we'll encounter even just in words, like the compressible fluids. So at least we'll have a background on this, although not in the very details. But I think the most commonly used property would be the density or weight density and pressure, and maybe a few on viscosity. Okay, so that's the reason why I only chose these properties. Okay, so other properties, we have surface tensions, what else, the capillary action maybe. So you can just read that in many fluid mechanics textbooks. All right, now we'll do problem solving for our fluid properties. Okay, so for the first one, we have this: the fuel tank of an automobile hold 0.098 meter cube. If it is full of gasoline having an SG of 0.78, calculate the weight of the gasoline. Okay, so we have a fuel tank, and it can hold, it says it can hold 0.098 meter cube, and this is volume. Okay, so if we right here, this is actually volume, and it is full of gasoline. So our substance is gasoline having an SG of 0.78. So calculate the weight of the gasoline. Okay, so we can write down our given, although this is a slower process, but if we are building skills, and we need to write it this way. Okay, so first, for the given, what is our substance? It says gasoline, right? And we'll write down our volume and our given specific gravity. Okay, so if you don't know where to start, if you don't know which equation, because we have a lot of equations, right? Now I guess we can just write down the equations for now regarding SG and regarding let's say density, right? Because if it's weight, then it must be related to some density. So if you write it down, we have the density, mass density, which is just mass over volume. So if you try this, you don't have the mass, right? Or you don't have the density of the gasoline, and we just have to rely on the data that's given. Now we're not yet allowed to look the values in the tables, right? So this is just computations. So we're only allowed to work on what we have. Okay, so we don't have the mass, we don't have the density, and therefore we cannot use this equation at the moment. So the next equation would be the SG. So the specific gravity is the ratio of the density of the gasoline and the density of the reference material. And since gasoline is a liquid, then our reference density is water, and that's equal to, this one is 1,000 kilogram per meter cube. Okay, so the density of gasoline, we don't have this, but we have this one, and we have the specific gravity, right? So meaning we can use this equation. And since this is just density, once we solve this density, then we can solve for the mass, right? And after that, once we solve for the mass, then we solve for the weight. Okay, so solution. For the solution, let's say solving for the density of the gasoline. Okay, so SG is equal to rho of the gasoline divided by the rho of water. So therefore SG, the given SG is 0.78 times 1,000 kilogram per meter cube is equal to the rho of gasoline. And if you do the math, we get a 780 kilogram per meter cube. Okay, the next step, I can just write 1, and then this one. The next step is to solve for the mass, right? So since we have this equation, density is equal to mass over volume, then mass is just simply equal to the density times the volume, and our density is 780 kilograms per meter cube times the volume of 0.098 meter cube, and we cancel these units and we get 76.44. And therefore, right, therefore the mass, the weight is weight is equal to mg, so 76.44 kg times the 9.81 meters. Okay, so the weight is 749.87 newtons. Okay, so actually you can I mean, if you have developed skills already, then you can do it faster, right? So these are just practice for building up our skills and presentation of homeworks. Okay, so let's do another problem. Okay, another problem is with regard to viscosity. It says here an oil has a kinematic viscosity of 1.25, that's E, which means exponents, or times 10 to the negative 4 meters squared per second, and a specific gravity of 0.8. What is its dynamic viscosity in kilogram per meter seconds? Okay, so for the given, we have the substance, that's oil, and we have our kinematic viscosity of 1.25, times 10 to the negative 4 meters squared per second, and our SG of 0.8. Now our working equation is this. We have a dynamic viscosity related to this kinematic viscosity by the property, by the density property, right? So we're asked to solve for this, but we don't have the density. We have this, so two unknowns, one equation. We cannot solve that. So therefore, we'll use another equation, which is the SG, right? The density of the oil all over the density of the water. Okay, so number one, so solve for density of the oil. Okay, so we have SG is equal to the density of the oil over water. So rho of oil is just simply 0.8 times 1000 kilogram per meter cube, and we get 800 kilograms per meter cube. Okay, now we'll solve for mu. So mu, or let's say here, solve for mu. So our viscosity is just equal to the kinematic viscosity times the density, which is 1.25 times 10 to the negative 4 meters squared seconds times the density, 800 kilogram per meter cube, and we get 0.1 kilogram meters second. Okay, so these are just basic problems regarding fluid properties. Now let's do our last problem for compressibility. Okay, a liquid is compressed in a cylinder of a volume of 2.0 feet cube under a pressure of 100 psi. When compressed at 180 psi, it has a value of 1.8 feet cube. Estimate the bulk modulus of the liquid. So we have a change. Let's say at condition 1, we have 2.0 feet cube at a pressure of 100 psi. So we can just write, okay, so we'll write given, and then we can tabulate we can tabulate the data. So we have condition 1 and then condition 2, and we have the pressure and the volume. So for pressure 1, it says here 100 psi, and our volume is 2.0 feet cube. But for condition number 2, when compressed at 180 psi, we have a value of 1.8 feet cube. Okay, so we have a larger volume here and a decreased volume here when compressed. Okay, so our equation would be E is just simply delta P over delta V over V sub 1. Okay, so for the solution, we can solve for delta P and delta V. Okay, so delta P is just simply P sub 2 minus P sub 1. So our P sub 2 is 180 minus 100, 180 psi minus 100 psi. So we have 80 pounds per square inch, and we can since this is in feet and this one is in inch, so we should convert this one into feet. So it should be feet squared, so times 12 over 1 feet, and we have to square this, and what you get is a value of 11,520 PSF, that's pounds per square foot. Okay, so therefore, solving now for E. So E is just simply delta P, which is 11520 PSF, all over, we need delta V as well. Delta V is 1.8 minus 2.0. So 1.8 minus 2.0, and recall that this must have a negative sign. Okay, and it's always, if it's delta, it should be 0.2 minus 0.1, or your reference, right? Your final condition minus the initial condition. Okay, this one would be, if we divide this by our original volume, which is 2.0, so that's gonna be that's going to be negative 0.1. Okay, so therefore our E, negative 0.1, no, that's negative. This is negative times the negative, so you have a positive, right? So therefore E would be 200 PSF. Okay, so these are just basic problems, and it is possible that in our homeworks we'll use a little bit harder problems, I mean, that requires analysis and thinking skills. Okay, so again, in our homeworks, please follow the solution guidelines. And even though I have shown you an example output of a student, it's not that I cannot do it, but rather the reason why I really impose the presentation is because I myself can actually do it as well. And so this is my output in one of my on my graduate course, let's say heat transfer. So this is how I present my solutions, right? So it's the same thing, drawing the resistance diagram, solving for the BU number, that's heat transfer, right? And that's it. So in the next video we will start a new topic, which is pressure and the hydrostatic equations. All right, so see you in the next video.